We consider the problem of phase retrieval when the signal being imaged is subject to a convolution with an unknown point spread function. Mathematically, the problem is to recover real or complex vectors x and w from the absolute value of the Fourier transform of their circular convolution. We will analyze the real-valued case, though the method extends to the complex case. This problem can arise in visible light communications and coherent light imaging. It is challenging because there is information loss in two different ways. First, only the product of the Fourier coefficients of x and w are measured. Second, only the absolute value and not the complex phase is measured. Information loss like these are common in problems from computer science, for example, sparse coding, dictionary learning, and non-negative matrix factorization. To have well-posedness, we will assume that w and x live in known low-dimensional subspaces of RL. We introduce a novel convex relaxation for this problem and provide a recovery guarantee with optimal sample complexity in the case that the two signals belong to known random subspaces. The problem can be posed in Fourier space as follows. Each measurement is the product of the square magnitude of a given vector acting on H and a given vector acting on M. The goal is then to recover these lower dimensional coefficients H and M. Using the standard trick of lifting, the quartic measurements in the unknowns H and M can be rewritten as quadratic measurements in the unknowns HH star and MM star, which we write as the matrices X1 and X2. Taking a standard semi-definite relaxation of this rank 1 matrix constraint, we arrive at the program, which is non-convex because of the hyperbolic constraints. We will use a convex relaxation called BranchHull. We observe that both terms in the hyperbolic constraint are positive because of the PSD constraint. Thus, the measurements always correspond to the first quadrant in the figure. As a result, we take the convex relaxation given by the convex whole of these measurements under the PSD constraint, which is given by the region above this hyperbola. The geometric picture of this convex program is as follows. The red region is defined by the hyperbolic constraints, the blue region by the PSD cone. The point of smallest trace lives on the pointy ridge of the hyperbolic constraint set that corresponds to having equalities in all of the hyperbolic constraints. We prove a theorem that if B and C have IID Gaussian entries, then the signal can be exactly recovered up to the fundamental global scaling ambiguity with high probability, provided that the number of measurements is almost linear and the number of unknowns. Numerical experiments show that the scaling constants are quite reasonable. Because of the difficulty of both the phase retrieval and blind deconvolution problems, it is important to interpret the provided algorithm and analysis with care. Nevertheless, we hope these results lead to additional algorithms for other problems with multiple sources of information loss.